In the early years of the Pacific War, Allied pilots fighting the Japanese Mitsubishi G4M, codenamed Betty, developed a grim nickname for it, the flying cigarette lighter. With just a few well-placed rounds, the sleek, twin-engine bomber would, with terrifying predictability, erupt into a fireball. It was a known, almost predictable vulnerability. But knowing something is flammable is one thing. Understanding why its designers would make it so is another. That understanding began not in the heat of a dogfight, but in the clinical silence of a hangar, where American intelligence officers and engineers finally got their hands on a mostly intact, captured Betty. What they discovered inside was not just a design flaw, but a window into the fundamentally different military and industrial philosophies that defined the enemy they were fighting. The Mitsubishi G4M Betty was one of the most ubiquitous and formidable Japanese aircraft of the war's early stages. It was the aircraft that had torpedoed the British battleships Prince of Wales and Repulse, a stunning demonstration of naval air power. It was a key component of the long-range strike forces that ranged across the vast expanses of the Pacific. To Allied pilots, it was a phantom, a fast, long-legged bomber that seemed to appear from nowhere, strike, and then vanish over the horizon. Its performance specifications, on paper, were impressive. It could fly over 1,800 miles without external tanks, a range that far exceeded most of its Allied counterparts at the time. It was fast, capable of over 265 miles per hour, and could carry a formidable bomb or torpedo load. But in combat, a different picture emerged. American fighter pilots, flying Grumman F-4F Wildcats, and later F-6F Hellcats, quickly noted a bizarre and fatal characteristic. When they engaged the Betty, their 50 caliber rounds, which might pepper a German Heinkel or an American B-17 without immediately fatal effect, would often cause the Japanese bomber to disintegrate in a massive explosion. It wasn't just that the fuel tanks caught fire. The entire aircraft seemed to be a flying fuel pod. The flying cigarette lighter moniker was earned because it lit with the ease of striking a match. One or two tracer rounds in the right place, and the aircraft was gone. This reputation created a tactical paradox. On one hand, the Betty was a feared and capable weapons system, the spearhead of Japanese naval aviation. On the other, it was known to be uniquely vulnerable. For Allied pilots, this was a tactical advantage. For Allied intelligence officers and aeronautical engineers, however, it was a profound puzzle. The fundamental principles of military aircraft design, by the 1940s, had converged on a few key survivability features. Self-sealing fuel tanks, layers of rubber that would swell and plug bullet holes, were considered standard. Armor plate to protect the pilot and vital systems was a given. The idea of sending a bomber into combat without these features seemed not just negligent, but illogical. Was it a manufacturing shortcut, a technological gap, or was it something else entirely? A deliberate choice born from a doctrine that viewed men and machines through a different lens. The only way to know was to get inside one. The opportunity to solve this puzzle came not from a dramatic aerial capture, but from the slow, grinding advance of Allied forces across the Pacific. As the Japanese perimeter contracted, they were forced to abandon advanced airfields, often in a hurry. It was on one such overrun airfield, likely in the Aleutians or New Guinea, that Allied ground troops discovered a Betty bomber that was largely intact. It may have been damaged and unable to fly, or simply lacking the fuel to escape. But for intelligence teams, it was a treasure trove. The process of securing the aircraft was a delicate operation. Japanese snipers and stragglers were often a threat in recently captured areas. The aircraft itself might be booby-trapped with explosive charges designed to deny it to the enemy. Once secured, the task of analysis began. The first step was always photography. Every inch of the aircraft, from the nose glazing to the tip of the twin tails, was photographed in meticulous detail. These images would be studied for any design changes, manufacturing techniques, or equipment fittings. Then came the real work. Disassembly. American engineers, working alongside translators, would systematically take the aircraft apart. They were not mechanics performing maintenance. They were surgeons performing an autopsy. Every component was examined, weighed, measured, and catalogued. The skin of the aircraft was studied for its alloy composition and thickness. The engines were dismantled to assess their horsepower, reliability, and materials. The electronics and radio equipment were analyzed for their frequency range and sophistication. But the most anticipated moment was the examination of the airframe's interior structure, specifically the wing sections where the main fuel tanks were housed. The captured Betty was often partially dismantled on site. Wings and tail sections were removed, and the entire airframe was crated for shipment back to the United States. This was a logistical challenge in itself, requiring transport to a port, loading onto a cargo ship, and a long voyage across the Pacific. Eventually, these prize specimens would arrive at technical intelligence centers, such as the Technical Air Intelligence Unit at NAS Anacostia in Washington, D.C., or at Wright Field in Ohio. Here, in the safety and quiet of a stateside hangar, far from the war, the most detailed and comprehensive analysis would take place. The mystery of the flying cigarette lighter was about to be solved, not by pilots in the air, but by engineers on the ground with wrenches and clipboards. Inside the hangar, under the bright lights, the Betty's design secrets were laid bare. The initial external examination confirmed its sleek, modern lines, but as the engineers began their internal inspection, their disbelief grew. The first and most glaring omission was the complete lack of self-sealing fuel tanks. Instead of the thick, multi-layered rubber bladders standard in American and British bombers, the Betty's fuel was held in simple, lightweight aluminum tanks. A 50 caliber round would punch a clean hole in the tank, and then the high-velocity slug would often create a second exit hole. This created a perfect spray of highly atomized aviation fuel directly into the oxygen-rich airflow of the wing. Any spark, from the impact itself, from striking an electrical wire, or from a tracer round, would instantly ignite this fuel-air mixture, leading to a catastrophic explosion that would tear the wing off or flash back through the entire fuselage. The second major discovery was the almost total absence of armor plate. In an American B-25 Mitchell or a B-17 Flying Fortress, the pilot and co-pilot sat behind thick steel plates. The dorsal and ventral gunners were protected by armored seats. Critical components were shielded. In the Betty, the crew sat in what was essentially a sheet metal tub. There was no protection for the pilots from fire coming from the front or sides. The gunners were completely exposed. The design philosophy seemed to be one of pure, unadulterated performance, with zero consideration for the survivability of the airframe or the men inside it once it was hit. Further investigation revealed the reason for this seemingly reckless design: weight savings. Every pound of self-sealing liner added weight. Every sheet of armor plate was a trade-off against range or bomb load. The Imperial Japanese Navy's specification for the G4M had demanded extreme range above all else. To meet this demand, Mitsubishi's designers sacrificed protection. The Betty was not designed to absorb punishment and return home. It was designed to get to a target far over the horizon and deliver its ordnance. The assumption, it seemed, was that its speed and defensive armament would be sufficient to protect it. Or, a more chilling conclusion began to form, that the lives of the crew were considered an expendable asset in the pursuit of the mission. The engineers looking at the bare aluminum tanks weren't just looking at a design flaw. They were looking at a cultural statement about the value of human life in wartime. The discoveries inside the Betty bomber were not isolated quirks. They were the direct result of a deeply ingrained design philosophy that governed Japanese military aviation in the early war years. This philosophy can be summarized as a doctrine of performance. For the Imperial Japanese Navy, which operated the Betty, the vast expanse of the Pacific was the primary strategic reality. To project power across this oceanic theater, range was not just a desirable characteristic. It was the single most important metric. Bombers and fighters needed to fly further than their opponents, able to strike targets and provide cover where the enemy could not. To achieve this phenomenal range with the engine technology of the era, designers at Mitsubishi and other firms were forced into an extreme regimen of weight saving. Every component was scrutinized, not for its durability or protective qualities, but for its mass. The airframe itself was built to be as light as possible, using thin-gauge aluminum and minimizing structural redundancies. The engines, while powerful, were pushed to their limits, and as the American engineers confirmed, the two heaviest contributors to weight, armor and self-sealing tanks, were simply left out of the equation. This was not a decision made in a vacuum. It was supported by a military doctrine that emphasized the first strike and offensive spirit. The ideal mission for a Betty was to locate the enemy fleet, deliver a devastating torpedo or bomb attack, and withdraw. The concept of a protracted slugging match where defensive durability was key was alien to this thinking. The aircraft was a samurai sword, designed for a single, decisive, killing blow, not for a brawl. There was also a cultural element at play, one that American engineers found difficult to quantify but impossible to ignore, a different valuation of human life and sacrifice. In the context of pre-war and early war Japanese militarism, the concept of gyokusai, shattering like a jewel rather than surviving in disgrace, held sway. The crew of a bomber was expected to achieve their mission, and their survival, while desirable, was secondary to that goal. The Betty was not a home to be returned to. It was a delivery system for a weapon, and the men inside were part of that system. This philosophy initially paid staggering dividends. The Betty's long range allowed Japan to project naval air power across Southeast Asia and the Central Pacific in a way that stunned the Allies. But as the war progressed and the initiative shifted, the flaw in this logic became apparent. The Betty, designed for offensive strikes against unescorted targets, was now forced into defensive roles, flying against ever-increasing numbers of radar-vectored, heavily armed American fighters. In this environment, its lack of protection was a death sentence. The design choices that gave it its strategic reach were the very same choices that made it tactically vulnerable. The Americans were building aircraft like the Grumman F-6F Hellcat, which was heavier, less maneuverable at low speeds than the Japanese Zero, but could absorb tremendous punishment and bring its pilot home. The two nations were building their weapons for two entirely different kinds of wars. The Japanese military was not blind to the Betty's catastrophic vulnerability. The pilots flying them and the commanders watching them fall from the sky in droves were acutely aware of the problem. As early as 1942, efforts were underway to create a new, better protected version of the bomber. The result was the G4M2 Model 22. This version featured a slightly different wing, more powerful engines, and, most importantly, self-sealing fuel tanks. But the solution created a new, insurmountable problem. The addition of hundreds of pounds of rubber lining and a small amount of armor plate had a dramatic effect on the aircraft's performance. Its range, the very reason for its existence, plummeted. Its top speed and climb rate also suffered. To the pilots, it felt like flying a different and inferior aircraft. The G4M2 was still vulnerable, just less so, and it had lost the exceptional quality that made the original Betty a strategic threat. Production of the new model was slow, hampered by Allied bombing, material shortages, and an industrial base that was not designed for rapid, large-scale redesigns. For every new G4M2 that rolled off the line, many of the old flammable G4M1s remained in service, their crews knowing full well they were flying a death trap. Other, more radical attempts were made to solve the range and vulnerability problem. One was the G4M3 Model 34, which featured further structural strengthening and redesigned fuel tanks that were better protected within the wing. But it was too little, too late, and produced in tiny numbers. The most extreme fix was not a fix at all, but a perversion of the original design's sacrificial nature. The use of the Betty as a launch platform for the Oka rocket-powered human-guided bomb. The already vulnerable bomber was now turned into a slow, cumbersome carrier for a piloted explosive, making it an even higher priority target for American fighters. The mission profile was a one-way trip, a final, grim acceptance of the aircraft's expendable role. The fundamental issue was that Japan's industrial and technological capacity could not easily reverse a foundational design choice. Retrofitting protection into an airframe not designed for it was a losing game. They lacked the vast reserves of strategic materials, like high-quality rubber and aluminum, that the United States could draw upon. They also lacked the luxury of time. While American designers were learning from combat reports and constantly introducing new, improved models like the B-29, which was a fortress of armor and self-sealing tanks, Japanese industry was struggling to sustain basic production, let alone implement a wholesale philosophical change. The Betty remained, until the very end, a testament to a brilliant initial concept that was fatally flawed in its execution, and which its creators lacked the means to fundamentally correct. For the United States, the technical intelligence gleaned from the Betty and other captured Japanese aircraft was of immense value. It went beyond simply understanding a specific enemy plane. It validated American design philosophy and provided a clear roadmap for how to fight the Pacific Air War. The analysis confirmed that American pilots should continue to target the wings and fuel tanks of Japanese bombers, as the payoff was disproportionately high. This knowledge was integrated into pilot training and tactical manuals, making every new Navy and Army Air Force pilot more effective in combat. Furthermore, the study of the Betty's weaknesses reinforced the American commitment to survivability. The lessons learned from dissecting the flying cigarette lighter were directly applied to American aircraft. The durability of the Grumman F-6F Hellcat and F-4U Corsair, the immense defensive capabilities of the B-17 and B-24, and the revolutionary, heavily protected design of the B-29 Superfortress were all, in a way, the antithesis of the Betty. American industrial might allow designers to have it both ways, to create aircraft with long range and heavy defensive armament, and extensive armor and self-sealing tanks. They did not have to make the brutal trade-off that crippled Japanese designs. The ultimate legacy of the Betty bomber is one of paradoxical brilliance and failure. It was an engineering marvel that achieved its primary goal of phenomenal range, a tool that allowed Japan to execute its stunning early war offensives. But its design was a product of a specific and ultimately flawed strategic moment. It was perfect for a short, victorious war. It was utterly unsuited for the long, brutal war of attrition that followed. When American engineers stood inside that captured hangar, looking at the unprotected fuel tanks, they weren't just seeing a design flaw. They were seeing the limitations of an entire military-industrial system. They saw an enemy that had bet everything on a first strike and had no plan for what came after. The Betty bomber, therefore, stands as a permanent lesson in the importance of balanced design, industrial depth, and the sober understanding that in war, the ability to endure punishment is often as important as the ability to deliver it.